Alright, this is part one of the unit on our Milky Way galaxy and other galaxies. We've talked about stars. We know their lifespans. We know the way they are born and live and die, even though they are technically not living things, obviously. But we know all about stars. And it turns out there's these giant conglomerations of stars called galaxies. And on the first page here, I want to basically tell you many of the answers without actually, and then what we'll do is we'll go into finding out how all this stuff was figured out, because it's only been very recently that we figured these things out. It turns out we live in a great wheel-shaped star system called the Milky Way. And the reason it was called the Milky Way is that in ancient times it looked like a milky band of light arching across the sky. Generally, it's very difficult to see the Milky Way in the modern world because of light pollution. Too many artificial lights bother our view of the sky. But if you go to a nice dark location, especially late summer, early autumn, you will see this band of light stretching across the sky. It looks a little bit like cirrus clouds in the sky. But in fact, it's the light of millions and millions of distant stars all blended together. And it turns out our sun is only one of these billions of stars. We think there's, give or take, a factor of 2, about 200 billion stars in our galaxy. Our galaxy is very difficult to understand the size of and the shape of because we live inside it. And mapping our galaxy has been a challenge for many, well, it's been a challenge for centuries. But it turns out we now know that our galaxy is around 100,000 light years wide. So even if we knew there was another civilization on the other side of our galaxy, if we tried to say hello to it, it would take 200,000 years to get an answer. It's a really big place, and we're pretty much stuck where we are. It also means there's no way we could send a spacecraft above or below the Milky Way or to the side of the Milky Way to get a good picture of it. So we're inside, and we have to try to figure out what it looks like from the inside. It turns out our sun orbits once every 250 million years. Okay, so we're actually moving through the galaxy, but all the other stars are moving too. Our galaxy is a big wheel-shaped system, as I said, and most of the stars sort of orbit around the center of the galaxy, more or less in unison. There are some outliers, and different stars at different distances orbit at different speeds. So it's not all synchronized, but for the most part, the material in our disk goes round and round the center of our galaxy, and at our distance, we go around about every 250 million years. A good analogy at trying to figure out what our galaxy looks like is, imagine if you wanted to try to draw a map of New York City from Central Park. You're standing there in the center of the park. You see all these large buildings surrounding the park. You have an idea about how big the park is. Have an idea how big the buildings are. You can see the gaps where the avenues go north and south. You can see the gaps where the streets go east to west. So you might get a rough idea of the construction of the city, at least in the general area of Central Park. But getting a detailed map of, say, Midtown or Wall Street would be very difficult. In fact, impossible, because we can't see through the buildings and we don't have a good perspective because we're stuck inside. It's similar with our Milky Way. Okay. It turns out, however, that our galaxy is really one of billions of galaxies in our universe, so it's not unique, and we'll figure out how that happened, how we found that out in a little while. Because the size and structure of our galaxy, as well as other galaxies, was a mystery just a century ago. So it really has only been in the last century that we've understood all this stuff, and there's still a lot more to understand. Okay. So, again, the size of the galaxy is difficult because, first of all, we're inside it. Secondly, it's a dusty place. Because of obscuring dust, using that analogy with Central Park, you can think of the trees and the buildings as sort of the dust in our galaxy. It obscures our view of distant areas. If the buildings were transparent, we might have a better idea or a better shot of seeing things in the distant parts of the Milky Way. But there is a lot of dust, and visible light anyway has trouble making it through the dust. However, as we know from the first part of the course, we can use other wavelengths of light to see different things. For example, infrared and radio waves can penetrate galactic dust, and so we can see farther in our galaxy with those wavelengths of invisible light than we can with regular optical or visible light. This is a picture taken from the IRAS spacecraft, the Infrared Astronomical Satellite. It's a panorama of our galaxy from the inside, and you can see it looks almost like a kind of like a double fried egg. You've got the bulge here in the middle, or it should be like the yolk of an egg, and then you've got the flat part here. The reddish orange stuff here is red giant stars and the glowing dust clouds in our galaxy. And same thing, the bulge of our galaxy here is made primarily of old cool stars. Still, though, it's hard for us to get distances within our galaxy, up until recently anyway. Getting that third dimension of space has always been a tremendous challenge. And when we talk about the vast distances, like 100,000 years from one edge to the other of a galaxy, we need a new type of distance indicator. Distance indicator, sometimes called a standard candle, is something that you can use to judge distances in space. You remember from our unit on stars that the only direct way to do that with stars is geometric parallax, and then we can use spectroscopic parallax and various other methods to find more distant things. Well, it turns out that nature provides us with a handy tool for finding distances, and they're called variable stars. We didn't really talk about this when we were talking about the evolution of giant stars, because frankly there was plenty to talk about and not enough time to go through every detail. But it turns out that giant stars go through a variable star phase. This is an instability stage. This variable star stage is where the star pulsates and releases extra energy after it pulsates. And so it pulsates in size, temperature, and brightness, and it varies its brightness in a sort of a regular way. It's almost like a balloon slowly filling up and then a valve opening when it gets a certain size, and then letting some air out and then filling up again. Except in this case we're talking about light or luminosity of the star being ejected. Okay, so the brightness variation of this star, which is called delta Cepheid, it varies from 3.6 to 4.3 magnitudes. Okay, so that's almost a factor of 2. It really changes its brightness noticeably, but it has a very regular period of 5.4 days, and then it repeats, and it repeats. So it gets dimmer, and then it gets brighter, and then it gets dimmer again. And the period between valleys or peaks of this variation is about 5 days. Now this is not the case for all variable stars. They have different periods and they have different brightnesses. But a very important discovery was made back at the turn of the century, not this past turn of the century, but at the beginning of the 20th century, by some astronomers at the Harvard University Observatory. They observed stars in the Large Magellanic Cloud. Now, the Large Magellanic Cloud, it turns out, is actually a small, irregular galaxy that is fairly close to us as galaxies go. Now, that doesn't mean it's close to us. It means it's about 160,000 light years away from our best estimates. And that's a long way away, and it's also much farther distance than the size of this small galaxy. So what that means is that when you look at stars in this galaxy, the difference in brightness, say, between this star and this star, or this star and this star in the galaxy, is the same as its actual difference in brightness, because they're all pretty much at the same distance. The distance effect doesn't really matter here, as long as the star is in that irregular galaxy. And that turned out to be very, very useful. It's kind of like saying, I have two friends who live in St. Louis. There's one that lives on the east side of St. Louis and one that lives on the west side. How far away are they from me? Well, it doesn't matter if it's on the east side or the west side. St. Louis is so far away from us that, for all practical purposes, they're both at the same distance. If you could somehow see your way to St. Louis with binoculars, we can't do that because of the curvature of the Earth. But if we could, and your two friends were shining a flashlight at us, those flashlights, if they were identical, would look the same brightness because there's not much difference in the distance. Well, an astronomer by the name of Henrietta Leavitt in 1912 was studying variable stars, the type of variable star that's named after Delta Cephei, the one I just showed you in a previous slide. She was studying Cepheid variable stars in the Large Magellanic Cloud and found a period luminosity relation. You saw that sort of sawtooth repetitive curve that I showed you. Well, it turns out that sawtooth curve is slightly different for different stars. Some stars have a long period. This one goes from like 15 to 55 days, so that's like a 40-day period. This one here goes from about 13 to 40-ish. Okay, so that's, I can't do the math, do the arithmetic in my head, but it's a much shorter period. This one here, for example, goes from 5 to 15, so this is only about 10 days. What Henrietta Leavitt showed, and the vertical axis on this chart shows apparent magnitude, and since they're all the same difference, all the same distance, apparent magnitude here would be proportional to the absolute brightness as well. And so basically anything up here is brighter than here. So this is the brightest, this is less bright, this one's dimmer, and this one is the dimmest. Okay? So long period variables are brighter. And the short period variables are dimmer. So because the Large Magellanic Cloud is so far away, these stars are all at similar distances, so the period of these variable stars are correlated with their intrinsic or actual brightness. In other words, if we can somehow calibrate them to see what their actual brightness is, we know what the actual brightness of this star is, for example. We would take the average. We could see how much brighter this star is compared to that. Okay, and we would know the actual brightness of both. And we could plot that on a chart. And it turns out these Cepheid variables are very, very bright. That's why we can see them at the vast distance of the Large Magellanic Cloud. But notice there's a very, very definite correlation. You can use a best fit line to fit your curve here. And actually, it's more like a line on this logarithmic graph. That shows that the longer the period, the brighter the star. Now, it turns out there's three types of variables. These are type 1 Cepheid variables. There's a different type of Cepheid variable that has a slightly different spectra, so we can identify it as a type 2 Cepheid, and that would have another type of chart. And then there are RR Lyra stars, which would be sort of down here. They're the dimmest of the three types, and they all have a similar period of around a day. So once a star's actual brightness or luminosity is known, its distance can be estimated from the star's apparent brightness. Okay. So in other words, if I know that this star here has a luminosity of, say, 7,000 suns, I can compare that to how bright it looks, and then I can actually get the distance to that star. And if it's in a cluster, or if it's in a distant, or if it's in a nearby galaxy, I can find the distance to that galaxy. All right. That's where we'll stop for part 1, and we will see in our next part how an astronomer by the name of Harlow Shapley used this information to try to figure out where we are inside our Milky Way galaxy.